Good morning, dear students. Welcome to another session of microwaves and antennas. So in today's session, we'll just go through the recap of what we had discussed in the previous session, and next we'll discuss regarding the reflex klystron, in which we'll be discussing regarding the mechanism of operation, then the modes of oscillation and the mode curves, and the analytical part of the output power. So there is no derivation involved in this. We'll be just discussing the analytical part over there. So in a previous session, we had discussed regarding the vacuum tube operations. So that is, we had discussed these things. So if we just see, we have interelectrode capacitances which are present, and then there are lead inductances which are present over here. So now here, what happens is, due to these lead inductances and the capacitances and the transit time, that is the three factors what we had discussed. That is, one is interelectrode capacitance, one is the lead inductance, and one is the transit time of the electrons. So transit time is nothing but time taken for an electron to move from cathode to the plate, from the cathode to the plate. So this was the plate side, this was the cathode, and this was the gate. So time taken by the electron to move from cathode to the plate is referred, time taken by the electron to move from cathode to the plate is referred to as the transit time. So when we move across, right, what happens is the transit time plays an important role. So we have, due to which there will be phase changes in the output which is available. So we have to cater to these issues when we are dealing with the high frequencies. Then apart from these, the interelectrode capacitances and the uh, lead inductances along with the interelectrode capacitances also pose a problem. So the interelectrode capacitances, what happens is, since they are acting as in parallel, so these interelectrode capacitances are imaginary capacitances. It is due to the space which is available over there. So now these capacitances will have some impedance value, and we know that this impedance is inversely proportional to the frequency. As the frequency increases, what happens? The capacitance, the impedance decreases, because it is a interelectrode capacitance what we are considering. So due to this, what happens is, we have uh, issues when we apply the input. So it will be like you are shorting this path and you are making the path available for it to flow around, due to which the overall output at the other end will be reduced. Now, apart from this, what happens is, the interelectrode capacitance and the lead inductances act in parallel. So it acts as a parallel LC circuit, and because it acts as a parallel LC circuit, what happens is it gives a feedback circuit. That is, for this entire vacuum tube, right? It acts as a feedback circuit, but the feedback is negative. That is degenerative feedback. So this degenerative feedback, what it does is it reduces the overall efficiency of this entire vacuum tube. So these are few of the issues what we had discussed in the previous session. So these are the problems what come up when we go for higher frequencies. If the frequency is low, what happens is interelectrode capacitance effect will be reduced. But when we go for higher frequencies, right, this poses a problem. Then LC circuit which is acting in parallel, that is interelectrode capacitance and the lead inductance, will pose a problem over there. So due to which, what we do is, we try to adjust some parameters of this vacuum tubes so that we can operate this entire vacuum tube at a very high frequency. So even with all the adjustments, that is, we try to adjust the distance between the electrodes, that is anode and cathode, so that the transit time can be adhered. So these are few adjustments what we try to do, but at the max, we will be able to reach up to say 1 gigahertz of operation. Above that, again, it poses problems. So only 1 gigahertz is not sufficient, because microwave range is very high. It is in the range of gigahertz itself. So it can be 1 to 10 14 gigahertz, whatever is available over there. So we'll be discussing regarding these also in the coming forth sessions. So at high frequencies, what happens is these are problems. So we have to look out for some alternate operations or alternate devices. So as we go ahead, right, say in the coming forth modules or coming forth sessions, we'll be discussing regarding a few of the microwave devices, how we can make devices operate in the microwave range, and what are the changes which are incorporated in them. So those all we'll be discussing. So these are the problems when we go ahead with very high frequencies. So next part which comes is klystron. So klystron is a device which helps us to generate microwave frequencies. It helps us to generate the microwave frequencies. Now, we basically have two types of klystron tubes. One is called as reflex klystron, and the other one is called as the multi-cavity klystron. So here what we are seeing is a reflex klystron. So why it is called as reflex, you'll come to know because of the repeller voltage and the electrons. The electrons get repelled in this, and that reflex action is utilized over here to obtain the microwave output. So because of which it is termed as a reflex klystron. So now reflex klystron is utilized for low power microwave oscillator. It gives you a low power microwave. It acts as a low power microwave oscillator. So this is how it operates. Then what about multi-cavity? So here you can see that there is a cavity which is present. In multi-cavity, what happens is it will be, we can see in the coming forth sessions, we'll be discussing two cavity klystron, wherein we'll be having two cavities. We'll be having two cavities. So such kind of devices, that is a such kind of klystron, that is multi-cavity klystron, is basically used as a low power microwave amplifier. It is used as a low power microwave amplifier. This one, reflex klystron, is used as a oscillator, that is low power microwave oscillator, and multi-cavity reflex klystron is used as a low power microwave amplifier. So what is the basic functioning of this reflex klystron? So here we can see that we have this overall block which represents the reflex klystron. So this is single cavity reflex klystron. So it will be used as a low power microwave oscillator. So here we can see that there is a cathode which is present. There is a cavity which is represented. This is a cross section. This is a cross sectional view. It's a cross sectional view. So in that cross section, this is all what you can observe. Then we have a re-entrant resonant cavity. Then we have a repeller space, the repeller voltage, that is minus VR, which is applied to this plate, that is repeller plate. Then we have in between, we have the accelerating grid over here. And here we'll be getting the output, which will be a microwave signal. So what happens in the klystron? So first of all, what does the cathode do? It basically acts as an electron beam. It acts as a electron gun, you can specify. So what this does is this shoots the electrons or emits the electrons towards the cavity. It emits the electrons towards the uh, cavity, that is the grid. Now before going to the grid, you can see, it shoots it towards the cavity. Before entering into the cavity, you can see that there is a accelerating grid. So based on the potential what is applied over here, either you accelerate the electrons or decelerate the electrons. So you can control the acceleration of the electrons in this grid. So cathode has emitted the electrons. It passes through the grid. This grid, based on the applied voltage, it controls the acceleration of the electrons which are passing through this grid. After it passes through the grid, it passes through the cavity. Now, since the electrons are moving at a very high speed, what happens is it passes through this cavity. Then it reaches the repeller space. So, what is the repeller space? So it is the space between the repeller plate and the cavity. It is a space between the repeller plate and the cavity. Here you can see that it has represented this part. So it is a space between the repeller plate and the cavity over here. So this space is termed as repeller space. So once the electrons are being emitted from the cathode, it passes through the accelerating grid, wherein it changes the acceleration of the electrons. Once it reaches the cavity, because of its speed, it passes through this cavity, and it reaches the repeller space. Now in repeller space, what happens is you can see that this is a negative potential which is applied over here. Now electrons are also negative, and they are negatively charged. So what happens is when these electrons try to move towards the other end, what happens is because of the negative voltage applied to the repeller plate, these electrons get repelled back. They get repelled. They get repelled. So that's why it is termed as a repeller plate. So electrons repel back. So when the electrons repel back, what happens is you are suddenly changing the speed with which, or the acceleration with which, the electrons are moving, and the electrons are forced to change its direction. So when what happens is it moves in the other direction and reaches the cavity. Now here, so in next slide, we'll be seeing what actually is happening over here. So now just remember that electrons are shooted from the cathode. They move through the accelerating grid. After that, they pass through the cavity. Once they pass through the cavity, they reach the repeller space. In repeller space, they are repelled back into the cavity because of the negative potential which is applied to the repeller plate. And when they repel back, all the electrons get bunched at one point. So all the electrons which are available here, they get bunched at one point. This is called as electronic bunching. So now what happens is since suddenly you have the kinetic energy of the say electrons which are moving in the repeller space, suddenly you have changed it. So this kinetic energy has to be released at some point. So what happens is when bunching of these electrons happen, that kinetic energy is released in this position. So this one helps in generation of the microwave signal. Now here you can see that for the cavity, what you're doing is you are applying a DC supply. You are applying a DC supply. Now because you are applying a DC supply, what happens is since uh, since we are applying a DC supply, what happens is noise is present in this cavity. One second, sir. So what happens is since resonant cavity is applied with the DC voltage and noise is present in this resonant cavity. So due to this microwave AC signal is being generated. So what happens is because of this bunching of the electrons and the noise which is present over there, we'll be able to get oscillations which are in the range of microwave frequency. So these interactions help us to achieve the microwave signal. So this is the overview of its mechanism. So this is what is happening in the microwave devices. Now when we come to the original mechanism, so this is the overall circuit representation which we have for that microwave circuit. So here again you have the electron gun which is applied with cathode. So it is nothing but this part, what we have represented over here. Then we have a cavity. Then we have a cavity. So which is this AB, which is represented. Then after that, we have this repeller space, that is which is specified as length L. So L is the length of the repeller space. Then D is the dimension of this cavity. D is the dimension of this cavity. And the cavity is supplied with the DC voltage. And here you can see that you have the accelerating grid which is applied with this DC voltage, and you can control it say through a knob. So wherein you are rotating a say a potentiometer kind of thing. So what you're doing is you are trying to control the acceleration of the electrons which are passing through this grid. Now what is happening in these things? So these are the things which are available. So here, what is happening is, first of all, because of the DC supply, you will be having a RF field present over here. That is radio frequency field. RF is very low frequency. Microwave is higher frequency. So there is a RF field, and what happens is this cavity resonates at one particular frequency. So that resonant frequency will help us to obtain the microwave AC signal. So here, what is happening is due to the noise which is present in this cavity and the RF field which is present over there. So because of that, we are able to get the microwave AC signal in this resonant cavity. It is along with all these operations what we discussed previously. It is along with all these operations what we have discussed. So in this case, again, you can just recollect the same thing as we discussed over here, the same. So this is the mechanism of how the oscillations are being generated. So there is an electron gun. It shoots the electrons towards the accelerating grid. The electrons pass through the accelerating grid, and then they pass through the cavity. They pass through the cavity because their speed is high. Now what happens is, since RF field is present over here, RF field is present over here, and there is an oscillation which is present due to that, say, noise which is available. So here what happens is, based on where the electrons are interacting, so that is what they have shown by these dots. So these are the possible interactions. So these are the possible interactions. So this is the maximum value of interaction. This is the minimum value of interaction. That is, electron can meet the positive peak, electron can meet the negative peak, or electron can meet anywhere in between of this RF field. So due to this interaction, what happens is you will be having the bunching occurring at some points. So here, what happens is the electrons are shooted towards the accelerating grid. Once it moves through the accelerating grid, it passes through the cavity. So once it reaches the cavity, it moves into the repeller space. Now repeller is negatively charged. So you can see that negative terminal is applied over here. So since it is negatively charged, what happens is these electrons get repelled back. And what happens is they get interacted with any of these points. So here you can see that you can have a negative peak, you can have a positive peak. So depending on this distance, then depending on what voltage you have applied, so all those stuffs, right, depending on the beam voltage, that is the voltage which is applied to the electron, then depending on the repeller voltage, then the beam current. So all these things make these electrons interact at one particular point. So here they have just represented that all the electrons are getting interacted with the positive peak of this RF field. That is the oscillations. So now here what happens is this is called as electron bunching, because all the electrons which are passing, right, all the electrons, it is not only these three, it is the all the electrons which are passing, because of the repeller voltage, they all traverse and interact at the same point over here. So here what happens is you will be getting bunching of the electrons. Now since the electron speed is changed, or the acceleration is changed suddenly, its kinetic energy gets released in the cavity, and that kinetic energy is utilized for the microwave signal generation. So here what is basically happening is, So this is mechanism of oscillation. Now, due to this, what happens is you'll get different modes of operation. Now, why you get different modes is you get different modes because of several conditions. So you can observe that electrons are getting bunching at one point. So here, if I just continue this waveform, for example, so what happens is these electrons either can bunch at this point, they can bunch at this point, they can bunch at this point, this point. So they can bunch at any point. They can bunch at any point. It is not that it will be always bunching at this positive peak. So it can bunch between this highest value and it can bunch between the lowest value. And since there are oscillations, right, it will be continuing. So due to this, what happens is where the bunching is happening. So due to this, you'll be having different modes of oscillations in the reflex klystron. Now in this case, now what happens is, suppose the same thing is represented over here. Now what is happening is, this is the RF signal which is present. The electrons are shooted. Now there is one highest value of interaction of electron with this field and one lowest value of the field interacting with the electron. That is, electron interacts with the field which is represented at C. So this is the negative peak and this is the positive peak. So in between also the electrons can interact at any point. In between they can interact at any point. Now here what happens is, if you just observe, so whenever electron interacts as the positive peak, at the positive peak, this, what it does is, this accelerates the electrons. So it accelerates the electrons towards the repeller plate. It accelerates the electrons towards the repeller plate. Now when the electrons interact during the negative this thing, what happens is this decelerates the electrons which are moving into the repeller space. So at this point, when the electrons are interacting, they are getting accelerated when they're moving towards the repeller space, and when they're interacting at the negative point, right, they are getting decelerated when they are moving towards the repeller plate. So in between, it will be in between this acceleration and the deceleration values. So if electron interacts over here, it will be accelerated, but it will be less than that as compared to the electron which is interacted at the positive highest value. If it interacts at the say neutral point, that is when the field is zero, what happens is the electron will be moving unchanged. Its acceleration will be unchanged. It will be moving as it is. So here it is getting a higher boost. Here it is getting a lower boost, whereas here it is not changing its acceleration. Here acceleration is increasing. Here it is decreasing. Here it will be as it is. So if you just observe from here, acceleration will be higher. And as we move down, right, acceleration reduces. So based on the electron interaction with the field. So now due to this, that is what is represented over here. So let me take these three lines. So here what is happening is, so this is representing the movement of the electron which has interacted with the positive peak. So here what happens is, since it is accelerated, it will move a little longer distance in the repeller space. It will move a longer distance in the repeller space. But since there is a repeller which is applied, that is the negative potential which is present over there, what happens is this will be repelled back towards the cavity. So due to which its acceleration starts to reduce. And what happens is it will get repelled and get bunched at one point. Now similarly, what is happening to this one? So it is getting interacted with the negative peak of the field. Due to this, its acceleration is reduced. So that is, its acceleration is reduced. So due to that, it will travel certain amount of distance in the repeller space, but this distance will be lesser than the distance which is covered by the electron which is interacting at point A. But at the same time, what is happening? Repeller is repelling back this electron also. So due to that, again, it changes its path and there will be a trajectory which will again reach at the same point. So here what is happening? This electron traverses and it reaches back at some point because the repeller voltage is kept same. So here again, what happens? This one moves around and then gets interacted at this point. So similarly, if there are n number of electrons, so what will happen is they'll move, they will have a trajectory and they'll come at this point, because all the electrons are shooted from the same electron gun and they're accelerated by the same accelerating grid. All different electrons are not accelerated or decelerated at different points. So all will be moving with the same speed. Because of that, because of the interaction, they'll be changing over here. And based on that, the distance traveled by the electrons in the repeller space will be adjusted. So if you just observe, what is happening is the electron which is interacting at positive peak is traversing a longer distance, but it is taking same amount of time to reach this point. It is taking some time to reach this point. So all these electrons will be reaching at same point. So this, because of this bunching, we get the microwave AC signal. Now here, what happens is, so based on where these electrons are getting bunched. So here we are showing that it is getting bunched at positive peak. Now there is a chance that these electrons can bunch at this point. These electrons can bunch at this point. These electrons can bunch at this point. It can bunch at any point. So based on where the bunching is happening, the output power is decided. Now, for example, if I just consider, if the bunching happens at the positive peak, if the bunching happens at the positive peak, what happens is the output power will be high. If the bunching happens at this point, say the negative peak, here the output power will be less. Here it will be the highest, here it will be the lowest. And intermediate, if the bunching happens, it will be in between these two. So based on this power and this power, it will be in between these two values. So it is not always that bunching will be happening at this point, but you can control, you can just observe how the bunching can happen over here. So you can control this. Now, depending on this, we have different modes of oscillations in klystron. So here you can see that so this is one entire cycle. So electrons pass. Say we'll be considering the highest value at present. We'll be considering that the bunching happens at the positive peak. So then again I have next one, another one positive peak. It can continue. So if the bunching happens immediately next to the next positive peak, we call it as 3/4 mode. If the bunching happens at the next positive peak, we call it as 1/3/4 mode. If the bunching happens at the third peak, first immediate peak, second immediate peak, and third immediate peak. So we call it as 2/3/4 mode, and it will continue. Generally, we can have maximum 4 modes possible. We can have 4 modes possible. So now in this case, you can see that the lowest mode is 3/4. Lowest mode is 3/4. So this is theoretical. This is theoretical. So generally it is difficult to get 3/4 mode. It is very difficult to get 3/4 mode in reflex klystron. So practically we'll be able to get 1/3/4 mode, which will be practically the lowest mode which is available, which is the lowest mode. So we have like 3/4, 3/4, 3/4, and so on. Generally 4 modes are available in reflex klystron. So theoretically, this is the lowest. Practically, when we see getting this one is difficult. So practically, when we observe, we have 1/3/4 mode, which is available. So this is the practical lowest mode possible. So there is another implication. Here, the lowest mode gives output power which is highest. So as we go on, for example, if this mode is available, so 3/4 mode's output power is greater compared to 1/3/4. Similarly, 1/3/4 output power is greater compared to 2/3/4, and it will continue. So as we increase the as we change the modes, right? So here what happens is the output power gets reduced. So this is what is happening in reflex klystron. Now in this case, there is another thing to identify, that is say how we adjust this modes. So we can adjust this modes by adjusting the repeller voltage, by adjusting the beam voltage, beam current. So these are just a few this thing by which we can adjust the by which we can obtain the modes. Now here another this thing to observe is, now if we are controlling it via the voltage, say a voltage which is applied to this electron gun and which we call as beam current and beam voltage, and voltage which is applied to the repeller plate. So we are controlling it through these. So we call it as electronic tuning. We call it as electronic tuning. Now there is another way you can control it, that is by controlling the length of the repeller. That is, I move this repeller either upwards or downwards, by which again I'll be able to control the modes. So this is actually called mechanical tuning. This is called as mechanical tuning. So this is what is happening. This is what is happening in say modes of oscillation. So in next class we'll discuss say the mode curve, which is relevant to this discussion itself. That is in short, if you just observe, so repeller voltage is negative. So this is the negative axis. So here also it is the negative axis. So this is the output power. So as I specified, the lowest mode gives you the highest output power. So here you can see that power output what they have specified. So this output power is higher compared to this mode. This output power is higher compared to this mode. So you can see that as the modes keep on increasing, the output power keeps on reducing. Now here you can see that here they have specified that the microwave signal which is being generated, it is in the range of, that is, this is the bandwidth. This is the bandwidth. So its bandwidth is around 10 megahertz. As we go on increasing the modes, right, we'll be able to get higher bandwidths. So that is another observation what you can look out for. So this is what we'll be discussing in the coming fourth session. So once we are done with this, we'll have a general discussion regarding the equations, and we'll solve one or two problems related to this. Okay. So this is all for today. Let us meet in the next session.